Okay, so we talked before about the end behaviors, and we know that we take the end behaviors from the right or to the left. So when x goes to infinity, f of x goes to infinity or negative infinity, vice versa. If x goes to negative infinity, uh, f of x goes to infinity or negative infinity. And rational functions, uh, the issue here is a little different because in rational function we have a restricted value. That means that we may have a two direction for x to go to the restricted value, one from the right and one from the left. So in this way, we have an extra way to describe the behaviors of the function. In other words, the rational function might have four different behaviors, unlike the quadratic function that has only two different behaviors, one with infinity and one with negative infinity. So let's talk about that. So I'm going to share a screen here, and we go through that. Okay, so so in your paper, I'm going to define the function f of x equals 1 over x. So when I say, for the notation here, when x goes to infinity, remember that we talked about that before, that means that if I have x here, that's negative infinity, and here is y, here is infinity and negative infinity. When x goes to infinity, that means x goes that way. Okay, and when x goes to negative infinity, I test the behaviors when x goes to negative infinity. But now I'm going to add a new thing and would say that, okay, suppose that I have a restricted value at a point C. And let's say that the C is a positive point. I'm going to go and define the C point here. Okay, C. And because it's a restricted value, I'm going to make a vertical line here. So I'm going to make this vertical line. So now, when I was talking about x, I said that, okay, x goes to infinity here, or x goes to negative infinity. But what about c? There is two ways to approach c. So either from the left this way, or from the right. So now I have two different ways to approach c. So x can approach c from the negative side or from the positive side. So here I can say that x approaches c from the negative side, and I put the negative on the top of c. So when you see c a negative on the top of it, that means that x approaches c from the negative side. And similarly, for the positive side, if x approaches c from the positive side, I say that x approaches c plus. Okay, I hope that it's clear for you. And let's get an example about one of the common rational functions, which is f of 1 over x, f of x equal 1 over x. So let's graph this function first. I'll try to find a good way to graph it. Okay, let's graph it in red. Let's do it here. Here is f of x equals 1 over x. So here is negative infinity, and for y-axis, infinity and negative infinity. Okay. If you look at the first example here, when we describe C, here's my C is 0. Do you see this is stand line, or the vertical line is 0. So I'm going to put 0 here. Let's say here with green, this is a 0. So now C is 0. So I'm going to describe here 4 points, x when x goes to infinity, negative infinity, 0 minus, and 0 plus. So let's do that. So we're going to test the behaviors together. So when x goes to infinity, f of x goes to where? And when I say goes, you must do this arrow. Don't say equal, because it's not equal. Okay? So when x goes to infinity, let's follow x here. When x goes, the x-axis, x goes to infinity. Where does that curve go? So it goes from infinity down, 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 and it approaches, and watch the y-axis. Don't look at the x-axis. Where does the y-axis go? Oh, it approaches 0. So then f of x goes to 0. Okay, let's test when x goes to negative infinity. What happens when f goes to negative infinity? X goes to negative infinity. So here's x, and goes to negative infinity. Let's follow the curve. It goes from negative infinity up, 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 and goes to again to 0. And here you watch y-axis, don't watch x-axis. F of x is y, is always y. So here's f of x goes to, again, to 0. Is that clear so far? Okay, so the next two things, and the new things for the rational function, I say that when x goes to 0 from the negative side, where f of x goes to. Let's see. So where is the negative side? This is a negative side. So I'm following x when x goes to 0. Okay? So I'm following the function f of x when it goes to 0. When it approaches 0, f of x goes to, follow the y-axis. F of x goes to negative infinity. Correct. Let's try when x goes to 0 positive. F of x goes to where? Again, let's do that. Here is a positive, so I'm going to go from infinity to the 0 from the positive side. And here x, this is a 0, 0 plus. So I'm going to follow the function. It goes to infinity. Okay? I hope this is clear. Okay, so based on that, I am going to call this line, which is x0, is a vertical asymptote. So now I have to explain what is the vertical asymptote is. So notice that when I went to 0, that the function f of x goes to either negative infinity or infinity. Therefore, I can define that the vertical asymptote is the line where the function goes either to infinity or negative infinity. Okay, so let's define that. The vertical asymptote, here's a vertical asymptote. So x equals c, and here's my problem, x equals 0, is a vertical asymptote if the graph of f of x goes to infinity, or f of x goes to negative infinity. Is that clear? Here again, the graph of f of x, here it is. At 0, here it goes to infinity, and here it goes to negative infinity. Therefore, x equals 0, this line, x equals 0, is a vertical asymptote. So how did we get the vertical asymptote? So if I go back to this problem, here is x. You set x to 0 here, the denominator to 0, and x equals 0 is a vertical asymptote. So let's see the steps how to find the vertical asymptote. So there are 2 steps, and it's already on your notes. I'm going to write them down again. Number 1, reduce the function. What does reduce the function mean? You simplify the function. My function is f of x equals p of x over q of x. So p of x is always the numerator, and q of x is the denominator. And again, q of x cannot be 0. Okay, so simplify it, meaning that if I have any factor that could be canceled out in the numerator with the denominator, I should do this as a first step. Number 2, we set q of x equals 0 and solve for x. Then the value of x, when I say x equals c, where c is a value of x, is the vertical asymptote. Okay, question. Can I have more than one vertical asymptote? The answer is yes. If you have more than value of x in the denominator, yes, you can have more than restricted values, and each restricted value is considered a vertical asymptote. Okay, let's see an example about that. So here's my example 3 in your notes. I have f of x equal 5 over x plus 3. All right, is there a way, so look at the 2 steps. Step number 1 here. Is there any way to simplify this function? I don't think so. It's 5x plus 3, so there is no way to simplify this function. So I'm done with step 1. Step 2, the set q of x is 0. Where is q of x here? It is x plus 3 is my q of x. So I set that to 0 and solve for x. Okay, so x plus 3 equals 0, then I get x equal negative 3. And this is my vertical asymptote. Okay, how do I graph vertical asymptote? So the way to do that, I don't know, I can like this way. Okay. Okay, so the way to graph the vertical asymptote, I'll go to negative 3 here, and then you graph a vertical line, and this is x equal negative 3. So this is my vertical asymptote. So if you have that, how can you graph the function 5 over x plus 3? We're going to learn about that in next section, or by the end of this lectures, and it's going to be something like that. I'm going to show it to you, but it's not going to be accurate, but I want to show you how you graph it. So that's going to be like that. Okay, so you're going to go, excuse me, we're going to go about the vertical asymptote. I'm sorry, that should be the opposite. That should be like that. So if you compare between this one and f of x is 1 over x, it's almost the same, but the function is shifted by 3 points to the left. Okay? Okay, I'm gonna erase this for right now, and we're gonna learn about it later. Let's get another example of the vertical asymptote. Okay, f of x equals x plus 9 over x squared minus 81. All right, so first step is to factor and find a way to simplify. So I have f of x equal x plus 9, and here is x squared minus 81. That could be factored as x minus 9 times x plus 9. Can you tell me why? The reason of that is this x squared minus 81 is a difference between two squares. X squared is a perfect square. 81 is a perfect square. Square root of 81 is 9. So the factor would be the two conjugate x minus 9 and x plus 9. Okay, x minus 9 times x plus 9. But hey, is there a way to simplify that? X plus 9 and x plus 9, we can simplify them together. So I can simplify x plus 9 with x plus 9. So what do I have in the numerator? X plus 9 divided by x plus 9 is 1. So f of x, not 0, because some of you said 0, is 1 over x minus 9. Okay? And now we're done with step 1. Step 2 is set q of x. This is q of x. What's my q of x right now? X minus 9 to 0 and solve for x. So x minus 9 equal 0. Therefore, x, when I add 9 to both sides, is 9. And x equal 9 is my vertical asymptote. Okay, let's graph that. So first thing, point 9 here, and do the vertical asymptote. I'm gonna make it in red. Okay, and then graph the function around the vertical asymptote in the shape of 1 over x. So I'm gonna do this way. Let's make it in green. Okay, so this is how we graph this function. This is a drafted graph. This I'm just trying to show you how to graph the function. And this is the function. So this is the function f of x is 1 over x minus 9, not the main function, the original function. The reason of that, I just want to let you know how to graph simple functions. Okay? So the vertical asymptote is one of the things that is important for graphing the function. Okay, so let's get one last example in vertical asymptotes. So I have here p of x is x minus 7 divided by 2x squared plus 5x plus 2. The idea here is that I have a quadratic denominator. So again, I need to factor that to see if I can simplify this quadratic denominator with x minus 7 or not. Okay, so I'm gonna go scratch work here, how to graph 2x squared plus 5x plus 2. I know some of you recommend uh, using a grouping here. So I can go with grouping. So 2 times 2 is 4. So I have 4. 2 times 2 is 4. So I need to find two numbers that makes two numbers. Their product is 4 and their sum is 5. So obviously 2 times 2 doesn't work, but 1 times 4 and 1 and 4 is 5. So I'm going to split this 2x cubed plus x plus 4x plus 2. And then group the first two terms and group the last two terms. So I have here. And I factor here, the common factor in the first one here is x. So I have x times 2, x squared. Oh, excuse me, this is squared, not cubed. Okay, let's fix that. So 2x plus 1 times 4x plus 2 here, the common factor is 2. So I have x or 2x plus 1. Okay, I factor 2x plus 1 and 2x plus 1. So I have 2x plus 1. And what is left is x plus 2. So this is the factor of 2x squared plus 5x plus 2. So I rewrite it down. P of x is x minus 7 over 2x plus 1 times x plus 2. Okay? So the question right now, I'm still in the first step. Is there a way to simplify x minus 7 with any factor in the denominator? So the answer is no. Therefore, I go to the second step and try to find the restricted values. So I set q of x, and where is q of x? It's 2x plus 1 times x plus 2 to 0 and solve for x. All right, so 2x plus 1 times x plus 2 equals 0. So I have here 2x plus 1 equals 0, or x plus 2 equals 0. So we subtract 1 from both sides. I have 2x is negative 1, divided by 2, x is negative 1/2. And here is, we subtract 2, so I have x is negative 2. Okay? So now how many vertical asymptotes do I have here? 1 and 2. So now I write down the vertical asymptotes. X is negative 1/2 and x is negative 2. Okay, let's graph these vertical asymptotes. So I have here both are in negative. I'm going to make it in green. So I have negative 2 and negative 1/2. So here is x equal negative 2 and x equal negative 1/2. I hope that this is clear how to graph these functions. We are not going to graph this function here, but I will stop by graphing the quadratic, I'm sorry, the vertical asymptotes, the two vertical asymptotes here. And by the end of this chapter or this section, we're going to learn how to graph a function like that. For the time being, I want to make sure that you understand how to find a vertical asymptote. If there's anything unclear, please don't hesitate to email me when we can set a session together and I can explain everything with you. All right, so I'm going to stop right now. I give you time to understand this, and then we go back to horizontal asymptotes. Thank you, and see you later.